Well, before I start, any questions? Anyone? Oh, yeah.
Where do I find the lecture slides?
You go under resources on Piazza. On Piazza, go under resources.
Oh,
Okay. And I think I don't have the one which I'm handing out right now. They are not there. I'll put it. But the other three are there. I do not have the recordings up yet in case you're looking for them, but the slides are there. Any other question? Okay, so last time we started looking into power consumption and sort of at a very generic level, electronics, the way it consumes power, I kind of had ended up with this kind of model, which one can apply at many different scales. So you can think of it applying to an individual gate or to an entire processor. But essentially, kind of the key components are there is power consumption which happens because computation is taking place or some activity is taking place. So clock is running and bits are switching when the clock is running. So either way, if we stop the clock or if we don't do any computation, as in keep feeding the same data values, so the data values are not changing, then this power consumption would be zero. So in one case, alpha would be zero, in another case, f would be zero. I can also shut off the power, so voltage can be made zero. C obviously is a function of the hardware, so you cannot affect that. The second one is the short circuit current, which is kind of similar. The only thing is now instead of the capacitor switching, the energy consumption is happening because there is a tiny amount of time when there is current which flows between the power and the ground through the resistances. So similar in concept, it's relatively tiny, but again, it's happening at every clock tick. Then there is leakage current, which happens because deep down the semiconductor sort of devices, they leak at the various diode junctions, and this is happening as long as you are powered up. So no dependence on frequency. So even if you stop the clock, this is still happening. And then finally, there is kind of other form of leakage happening, which basically refers to the fact that there might be other aspects of your system where because of circuit reasons you are consuming power. Like for example, maybe somewhere I have a very high resistance between power and ground, and therefore there is a continuous leakage happening. So analog circuits could be of that nature. So as long as we are powered up, again, this will keep happening. So main thing which sort of I want to emphasize is that it used to be that it's the first term which used to dominate, but increasingly it's the latter terms which dominate. In fact, for all practical purposes, you can basically say that, look, this second term is tiny, first term is roughly half, and this term is roughly half. Okay, that's kind of a good way of thinking about it. And whatever type of system you're looking at, you'll see something to this effect. Okay, so while I'm describing it in context of the circuits, but same concept applies to buildings or cars or any other kind of system. The other thing I sort of pointed out was that as technology scales, some of the effect on these terms is kind of different. So as microelectronics shrank, so did the supply voltage, and for reasons to just maintain the reliability of the circuits, and the net effect of, so that voltage has been going down, but it sort of has begun to plateau. And this particular gap between the supply voltage and the threshold voltage affects the speed of the circuit. So as you lower the voltage, it does come at a cost, namely things slow down. So to compensate for the slowdown, what is done is to lower the threshold voltage. Okay, so threshold voltage has been coming down, but there are limits to which you can go down. So it, like I said, it has plateaued. Main thing is that as you at a given threshold voltage, as you change the supply voltage, you are going to pay for it in delay. So as I lower the voltage, the delay rises and rises pretty steeply. Leakage, in turn, also depends upon the threshold voltage. So the bad news is that as to maintain the, to lower power, we lower VCC. To maintain the speed, we lower threshold voltage. But when we lower the threshold voltage, the leakage goes up exponentially. So there's a kind of an interesting trade-off which emerges, which is I can do things, so I can either keep leakage power same, lower the dynamic power and lose in speed, or to some extent I can lower the dynamic power, maintain the speed, but then pay for it in leakage power, okay? And it's that trade-off which kind of comes and hurts us. So bottom line is all of this collectively basically at this stage has placed kind of a limit on how much further we can go. So the scaling related, technology scaling related benefits when it comes to power are kind of behind us. And by the way, this is only about electronics. If you're looking at, let's say, something like a radio, as we'll see later, the power consumption is also decided by the sheer ability to communicate. So sort of to maintain the requisite signal to noise ratio. So Shannon's equations and all, they kind of dictate that. So not everything is dictated by the same physics. If you're looking at other types of systems, there may be other similar equations that may come into play. So upshot of all of this is that the ratio of leakage to the total has been going up very rapidly, and it's basically kind of hit the 50-50 point at a few technology generations ago. That's 65 nanometer technology. Just sort of curiosity, anyone knows what feature size we currently make chips at? Yeah, 22. There even 14. Or even some DRAMs are at 10 or 11. So, but 22 is very common. But like 14 has begun to creep into the marketplace. Okay, so several generations ago, basically we kind of hit this limit already. Now, so much of the power management now actually is determined by this leakage current. The fact that the sheer act of keeping a circuit on burns a significant amount of power, whether you actually do any computation on it or not. So what's happening is, so let's look at where the effect would be higher. So let's say I have to do some computation, and I have two choices. I can run at a fast frequency, or I can run at a low frequency. When I'm running and I'm doing the same number of instructions, so same n instructions I have to do, in one case I'm going to do it more quickly, n clock cycles very rapidly done, in the other case n clock cycles slowly done. What will happen is that in case of the slower clock cycle case, the leakage current is going to, you are going to integrate the effect of leakage power over a longer time period. So while I have the same number of clock ticks, right, but I have stretched them out. So if you look in terms of how things may pan out if I am if I duty cycle the system. So what I mean by that is, imagine what I'm doing is that I turn the system, I run the system for a while, do some computation, then sort of idle it for a while. Okay, so I'm still on, but I'm not doing anything. Okay. So now, during that time, what will happen is that as time progresses, the leakage energy is going to continually increase because the system is on, it's powered up. Whereas the switching energy, the first term, that the dynamic energy, it is going to increase while the system is on, and then for the time the system is idle, it's going to flatten out. So if you look at it this way, then essentially what it suggests is, from a leakage perspective, the proper strategy is to run as soon as possible and be done with it. Of course, the problem comes is that if we run very fast, that is, so looking at this picture, I can do one of two things. One is that I run as quickly as possible. That means I eliminate this dead time where I'm not doing any computation. My system is up. So I try to eliminate this dead time by doing things as soon as possible. But that may not always be the case. Imagine a system like where you have a new task arriving every time t. Okay, so every time t, I have a new sensor sample comes in, a new image comes in. So now you have time t to process that image. So you have one way you can approach this thing is to hog or occupy the entire time and set the frequency so that your finished time of your program corresponds to this. The other possibility is that I run at a faster frequency and then finish it sooner, but then I idle. Okay, and the third possibility is that I finish it as soon as possible, but then I power down the system. Okay, and that would mean wake it up at the right time. Well, if all I'm doing is to idle the system like this, so run fast and idle, what is happening is that leakage energy I'm still paying, but the dynamic energy actually going to increase because I'm going to be running at a faster clock, and therefore also to support the faster clock, I'm going to run it at a higher voltage. So when faced with something like this, and you are not allowed to power off the system, then leakage you have to pay anyway, and then you are better off running as slow as possible, this time limit per decimal. If on the other hand you can shut down the system, then your better strategy would be maybe to run quickly and then power off so that you save on the leakage. And the ratio between the two, switching and leakage, is going to affect the policy. So we're going to see that later on, but these two energies are often at tension. So what's happening out here is, this is a plot for some processor. So what you see out here is, in this dimension, there's a switching frequency. On the dimension into the board, it's a supply voltage, and what we are seeing is the energy out there. So what's happening now is that as the frequency goes up, the leakage energy will go down because I am going to finish more rapidly the same particular task. As the supply voltage goes up, leakage energy goes up, and the switching energy also sort of goes up. But if you look at the frequency side, as the frequency goes up, the switching energy will also go up because we have to sustain it. So they are often at odds with each other, and sort of your goal would be that you care about the total energy, so there has to be the summation of this one has to take into account. And if you look at the summation, there is going to be that for any given choice of let's say for any given choice of voltage or any given choice of frequency, there's going to be some optimum thing. So there's going to be some sort of an optimum curve which is going to go through this sort of summation space. And the goal in some senses would be to operate at that. And so if my leakage energy is very high, then clearly the solution would be run as quickly as possible, shut the system down. If on the other hand, if leakage energy is zero, then the optimum policy would be run as slow as possible to make use of the entire time. In general, it is going to be some balance between the two. So what all of that leads to then is, could we now make use of these insights into develop some sort of a model, some sort of a higher level model for, let's say, a processor. So ignoring kind of the other two types, the short circuit current and all, essentially we can say that the power consumption of a device like this is a function of voltage and frequency, and that is in turn made up of the switching component and the leakage component. And roughly speaking, so remember there was an alpha in the C term, so that will correspond to some constant. So there's some constant K1, V square F, that's the dynamic power, and some constant K2, V e to the power V3B. So this one is showing that there is an exponential dependence of leakage on voltage. So this is how this term is going to look like. Now, not every pair of voltage and frequency are possible. That is, if I give a voltage, there is going to be a corresponding maximum frequency possible. But you can always operate at a lower frequency if you so choose. So in early days, there were systems where voltage could not be changed, but frequency could be changed. So you could basically lower the frequency, but not affect the voltage. Do you think it's did they serve a purpose? Like, I mean, so let's say I give you a system where voltage cannot be changed. It is fixed at the board level, but frequency you can change. So is there any benefit to lowering the frequency? So let's look at the two components, right? I mean, so lowering the frequency means that I am going to do that n clock cycles. I'm running a program n clock cycles over a longer period of time, right? Voltage is the same, so clearly leakage power, leakage energy goes up, right? Because leakage power is what it is, but the integral I'm doing over a longer period of time. What about the dynamic power term? Well, frequency is going down, but I'm doing it over a longer period of time. So another way of thinking about it is going back to this model, that when I do energy, I am actually independent of the frequency, right? So energy to do an instruction is actually independent of the frequency. So the dynamic power consumption is going to even out, because what's happening is that I'm operating at a lower frequency, but I'm proportionately operating over a longer time. So the dynamic power consumption is actually independent of dynamic energy is independent of the frequency. So what will happen in a system, that kind of system, is that it's essentially a no-win thing, in the sense if you lower the frequency, you are just hurting yourself. Okay. So do you think there is still any benefit to lower the frequency? So as we discussed, from an energy perspective, it's a no-win. You can only lose, right? That dynamic energy contribution of dynamic power remains constant. Energy contribution of leakage goes up. Jeremy.
If you lower the frequency, you reduce the amount of heat that you're generating.
Exactly. So the secondary effects come into play, right? So you lower the amount of heat. So that's one possibility. You're also lowering the peak power, okay, which can have benefits also. Okay, so there are these kind of issues that can, these kind of secondary issues that can come into play. Going back out here, so my high-level model is like this. Okay, so we have basically taken all those alphas and C's and all and reduced them down to kind of the basic essence. And then essentially the problem boils down to that I have to fit this model into whatever task I'm doing on the processor. So let's say I'm running this processor on a program which then takes n clock cycles to run. Okay, and let's make all simplifying assumptions that it's a RISC processor, one instruction per clock cycle, and every instruction is essentially makes same power consumption. So they're all kind of fairly reasonable assumptions. For most processors, you don't see much variation instruction to instruction. There are processors where type of instruction matters, but those are a very good first order model is that all instructions are the same. Okay. So energy taken by a program which runs takes n clock cycles is going to be power term multiplied by n divided by f. So it's basically saying n clock cycles. Okay, that's the time duration. And therefore, I am going to end up with a term which looks like this. So see how the frequency term disappeared. So it's k1 n v squared, and here there is a frequency term out here. And you can think of this k1n as kind of like the total capacitance you are switching over the course of the program. Okay, so there's a single coefficient c. Let's say we call it c total, and then this additional term we can kind of write it like this as another coefficient. So, so that's one part. The other thing is, like I said, for a given voltage, there's going to be allowable frequency. Okay, you cannot exceed that, and so F max, so F max is the maximum frequency you can run it at. It doesn't mean that you are indeed running it at that, but it places an upper bound on F. So it looks like this, where again there are a couple of coefficients out here. So in a sense, now what happens is you can run the program and collect a lot of data and estimate these coefficients that we have, the C dot, the I naught, beta, K4, K5, essentially kind of a nonlinear regression problem that we have. So you make sort of simplifying assumptions like K5 is often assumed to be 1, you assume that V is much greater than threshold voltage, so you kind of ignore the threshold voltage part, things like that, but roughly speaking, so the way we run processors, there are a couple of, oh, go ahead, sorry.
Only one question about that. At the end of the day, generated heat will be a function. You will lose some energy when you generate heat. So it should be some function out of these parameters. It's not an extra parameter that we say, okay, if we decrease.
Okay, so fair point. So generated heat in terms of joules is certainly like it's just that oftentimes we care about generated the rate at which the heat is generated, because my cooling system would have limits on it. Okay, so what would happen is if I'm generating more heat than what my fan or cooling system can remove, then the temperature will go up and then bad things will happen. So given any system, there is usually a limit on how the rate at which you can generate the heat. So heat removal in itself is a non-issue if I have infinite time to do it. The problem is that the rate at which heat is generated is becoming becomes the issue. So that's where it's coming from. So you're right that heat is decided by whatever energy, whatever the heat energy is decided by that, but heat power depends is the consideration. So common cases for using this model, one is where we are doing voltage and frequency simultaneously. So kind of the idea is voltage is set so that corresponding Fmax is the frequency. So I essentially treat voltage as kind of like my knob, and if I lower the voltage, then the processor can only run at a smaller frequency, but I'll always run the processor at the fastest possible frequency. Now, that's easier said than done, because the fastest frequency you can run at a particular voltage depends on a lot of other factors too. It depends upon, for example, how hot it is right now. It depends upon what that particular chip is behaving like. I may buy 100 chips, 100 identical chips, and their Fmax for a given voltage would be slightly different. Then you also have issues like I may tell the system set the voltage to 5 volt, but in one case it may set it to 5 volt, the other case it might be 4.95 and all, because there are variations in the power supply itself. So upshot of all of that is that it's not easy to figure out what Fmax is. There are a couple of ways of doing it. You calibrate the system, create a table so that you have voltage frequency mapping, and then you take into account the temperature and all. Alternatively, there are circuit ways of doing it. So you could design a frequency generator which automatically will set the frequency such that it matches a certain delay. Okay, so you can design circuits like that. So this ability to do dynamic voltage frequency scaling, where you essentially set the voltage and then the frequency is automatically set to this corresponding frequency, corresponding Fmax, or vice versa. I set the frequency because I need a certain speed, and then the voltage is automatically set to that voltage. So that's often found in hardware now. The other possibility is the one which I was describing, which is dynamic frequency scaling. So voltage is fixed, and the frequency is selected to be Fmax or lower. Okay, and as we saw, it does not carry any energy advantage necessarily, but it can carry heat advantage, heat dissipation advantage. It can carry peak current advantage, and actually there is a third benefit it can have, is that batteries, which we'll see maybe later today, maybe next time we meet, is that if I have a battery with a certain number of joules in it, how many joules I'm actually able to extract out of it depends upon the rate at which I extract. So let me clarify. So let's say you buy a battery which claims to be, I don't know, 2000 milliamp hour. Okay, so it has certain amount of joules in it. If I operate it at 1 amp versus I operate it at half an amp, I'm going to, my effective capacity, that is how many joules I will actually be able to extract out of it before the battery effectively dies and have some unused chemical energy in it, that changes. And usually batteries do better if you draw current at a lower current, if you draw energy from it at a lower current. So there are those advantages which come into play. So this simple model, okay, I mean, we basically reduced all those thousands and millions of devices and within the processor and all to kind of essentially 4 or 5 constants. Turns out to be pretty well. So this is work out of MIT many years ago, and what you see is for different programs running on some data, so FFT, DCT, inverse DCT, FIR filter, computing log, and time delay least mean square. Okay, so what you see out here is that they measured the actual power consumption versus they computed the power consumption. They computed the C-tot and they computed thing, and the error is pretty good. I mean, they're basically within 5%, even with a simple model like this. Okay, so it goes on to show that you don't have to do energy accounting on a per transistor level and all. You can basically kind of take this complicated processor and reduce its energy to a very simple 5-parameter model. Okay, or possibly even lower. So ideally, what we would like to do is that when we are trying to do energy management, you want to create a model which is what you can say is a lower order model. That is a model which has very few parameters, very low dimensionality, because then you can reason about it and you can manage it effectively. So again, like let's say you're trying to model energy consumption in this building. You could certainly do it by taking into account every individual, every room and all, but it will kind of defeat the purpose. We'll have a horrendously complicated model. Could we reduce it down to very few parameters? And this is an example on how something complicated like a processor got reduced to a very simple model, and it still does the job pretty well. So in recent years, there's been a lot of work on, therefore, coming up with such power models. Just curious, so another question. So what good do you think, let's say, what are the different ways we can use a power model? Why bother power modeling? I guess that's what I'm asking. Any thoughts?
Designing the cooling system.
Okay, designing the cooling system. What else? Okay, policy making.
Scheduling background tasks on the computer.
Okay. How about estimating battery life before I run something, right? How about choosing between two programs, which one is more efficient? So there are all these other additional considerations where a model could come into play, or even things like, let's say I'm making a decision between processing locally versus sending it over and being processed remotely. So I may have to look into energy models of radio versus CPU and consider that. Okay, so variety of different reasons why sort of power model essentially are kind of essential for me to for one to be able to do good power management. Power consumption in computing systems. I just kind of stole it from Apple's website, as you can see. Thing I wanted to point out is that most of these systems are in many different modes. So they are off, and one thing you would see is that even in the off mode, they're actually consuming power. Okay, and this is the power of the power adapters. Okay, there is some, even when our computers are off, they still consume power also to maintain some other tiny little stuff. Okay, I mean sometimes the Ethernet card is remained on so that arriving packet can wake it up. Okay, there is also time being maintained in these systems, so there's still some stuff. I mean they're never truly off. Okay, there is sleep mode, and you can see now we are to a few watts. Idle mode, where the system is powered up but it's idling, it just has nothing to do. So deep within the operating system, the queue for doing any task is all empty. And then finally, this kind of number is interesting, which is the power efficiency of the adapter itself. So efficiency of the power supply, and you see it's kind of 90% out here. So which means every watt that I need for computation, another 0.1 watt, I have to just throw in the power supply system. This is for a iMac. Again, kind of similar kind of numbers that you would see. You could see that its sleep mode is more efficient. Okay, idle, but now this thing has a display, so sort of the power consumption is kind of on the higher side out here, 70, almost 80 watts. This is for a 13-inch MacBook Pro. When you look at so clearly the class of machine matters. If you look at servers, depending upon kind of mainframe versus blade versus, okay, you see kind of a different split between how much goes into processor, how much goes into memory, but the main part really is the power subsystem also consumes a significant amount. Roughly 30% of the power is going into the power supply itself out here. When you come into a laptop class system, so this is Calpella, which is one of those, I think i3 or i5 core type processor. So what you see out here is it running different programs as well as kind of sleeping. Okay, one thing you would see is that there is a constant offset, constant thing which is coming just because of the graphics system. The CPU part depends upon what you are actually doing. There is power being consumed, some amount of power being consumed by the fan. There is some amount of power being consumed by the network, the LAN out here. The level 3 cache, which is the level 3 cache and its controller, that is a significant contributor. So why do you think L3 cache is consuming so much power? It's a significant amount of power. Yeah, a lot of memory and a lot of very fast memory, right? I mean, so that's causing causing this issue out there. Then there are other chipsets like controllers, power management hardware itself. All those kind of things come into play out there. So that sort of one thing you would see is again kind of the display or the graphics subsystem. The graphics subsystem matters quite a bit, and in this particular case, actually the display power is not shown. So this is the GPU power, and then there will also be the display power. Go ahead.
Why would the graphics components consume power when
Sleep, because you still have to maintain the state. So I put it to sleep, I wake up, the graphics are still there. Okay, and also these are details which also depend upon the specific platform also. Okay, I mean, you could imagine that saving things up and bringing it back, right? So it depends upon, because restoring graphic state takes time, so you kind of just keep that thing up. So this is for an older laptop, and there are other things which sort of come into play out here. So this is, as you can see, kind of a Pentium M class stuff. Hard drive, okay, one thing that you would see with the hard drive is that you could put hard drive into idle or standby mode. In the standby mode, it kind of stops, okay, the disk stops spinning, and then kind of active mode. So hard drive has a fair number of modes. Display, again, you can affect its brightness level, and there is a direct sort of contribution because of that. Then there is a CPU power, and there is a CPU power under different operating systems, how they kind of make use of it. All these factors kind of come into play. I'm going to skip these. There are a lot of details in different decomposition. Point is that two takeaway messages from this. One is when it comes to laptops, the display matters quite a bit, and within the display, there are different kind of display technologies, and they play a role. So unlike server, display is a power consumer. The other thing is there's a huge dynamic range. It depends upon what you are doing on the laptop. So let's talk about the displays, because almost 30%, 40% of the power consumption can be just the displays. So if you can minimize the display power, battery life can improve. Now, most displays until relatively recently, and I guess on laptop class devices still are LCD displays. Whereas when it comes to smaller devices, tablets and phones and all, the OLED displays or organic LEDs are the one which sort of are becoming quite prominent now. So these two displays work in a very different fashion. So LCD displays are what are called as backlit displays. So what basically happens is there's a light behind the display, and what the LCD display is doing is when you turn on or off the pixel, then it basically either blocks the light or gets the light go through. So it is in itself not generating any light. The light is being provided by a backlight, and that is what you are seeing. So essentially, when you are seeing white color, then essentially the pixel is fully on. When you are seeing, let's say, the red color, then one of the subpixels is on. So there are 3 subpixels RGB. One of them is on, the remaining 2 are off. And when you're seeing black, all 3 are blocked. Okay. So key point out here is LCD power is not color dependent. It is brightness dependent, because I can change the brightness of the LCD thing, or I could change the opacity of the LCD optical transmittivity of the LCD pixels themselves. OLEDs work differently. They are what are called as emissive pixels. So each pixel emits light. And more importantly, since each pixel has an R pixel and a G pixel and a B pixel, you could also imagine that the color might matter, okay? Because, for example, if I have a pure red, then only the R pixel is on. If I am generating, let's say, something which is a combination of colors, then multiple subpixels have to be on. Moreover, not all our eyes are less sensitive to blue, so for the same degree of brightness, we need to generate it at a higher energy. Okay, so there are differences come into play because of that also. So these differences then play on to the way power management is done. For LCD displays, you basically, the control you have is backlighting control. So you can change the brightness, or you can shut the thing off. The LCD part itself doesn't consume as is not the major contributor. It's the backlight. In case of OLED, again you can change the brightness, but you can also muck around with the color because color matters. And you cannot change colors in photos and all, but you can certainly change it for the GUI elements and things like that. So for example, the newer Samsung phones have this mode where when the battery is close to dying, they kind of switch into a black and white mode. Okay, so that's an example there. But you could be more aggressive. There are color schemes which are more energy efficient than other color schemes. Okay, I mean clearly something which is white dominated is going to be more energy wasting than more energy consuming than the one which is not. Any other display technologies out there that you have heard of?
Don't they have new quantum dot ones coming out?
Yeah, I don't know what they do though. I've heard of them. Anyone knows? Okay. What else? Anyone heard of e-ink, which is used by some of the Kindles? Anyone? No? You have? No? Yeah, the way e-ink, so a disadvantage of both LCD and OLED is that when you shut off the graphics system and you shut off the display, when you power off the display, it basically loses the image. I mean, you cannot see anything. The way the e-ink works is that the image is persistent. So you can power off the display and it retains the image. Okay, so in applications where, like reading a book, where essentially the image changes relatively infrequently, and there are long periods of time where essentially you care about maintaining a persistent image, then in these applications I still have to keep supplying the energy all the time. Whereas in an e-ink type display, I can basically shut off. I can shut the power off to the display, but you will still see the image. The flip side is they are not emitting any light. So you can only read them in reflected light, right? There has to be ambient light to be able to read it. So if you are in a dark room, e-ink display doesn't help you. But on the other hand, they actually do very well if you are in like sunshine and all. In fact, these displays start having problems there, like a washed out display on your phone or your tablet when you're outside. So display power management depends upon the type of technology. Same issue that we had with CPU, which is we need to be able to power model it, model the power of this thing. So what would be a reasonable power model? So let's talk about, let's say LCD display. So what do you think would be a reasonable power model for an LCD display? So what we know about LCD is the following, right? That essentially I have a backlight. Each pixel, I have an R pixel, a G pixel, and a B pixel. And those pixels differ only in the sense that they have like a little filter in front of them, which lets red light through or the green light through or the blue light through. Okay, but other than that, sort of all pixels are basically the same. So firstly, color would not matter because the color is a matter of which pixel you are turning on, which subpixel which subpixel is on or off. Okay. But the backlight is the same. So what do you think would be a good power, intuitively a first order power model for a LCD display? Huh?
The brightness.
Okay, so brightness, and what else? Okay, so it's proportional to the number of pixels, right? So I could, okay, in the screen, okay. Could you do something to this display to improve its energy efficiency? How about creating a backlight which have multiple, like instead of a backlight, if I could control the backlight in different regions. Okay, so let's imagine that I can have a lot of independently controllable elements in the backlight. Then whenever the pixel is black, I can turn off the light out there. Okay. Of course, I cannot have a light behind every pixel, but I can have behind regions of the screen. So you could imagine, I mean, some of the TVs and all, which kind of advertise themselves having deeper blacks and all. What they actually do is they identify regions of the image where essentially the scene is black, and then turn those things off. So you could do those kind of things. What about the OLED? So in case of OLED, color matters. Okay, so you could imagine something like the following, that at the pixel level, I'm going to have some energy because of some power consumption because of R, some power consumption because of G, and some power consumption because of B. So now the way we work with these frame buffers is we send out an RGB value, which is usually 8 bits, so 0 through 255. So it's basically saying the R and G and B indicate the software visible sort of value that the pixel has, and then the actual energy is going to be some function of that. So the red OLEDs are going to consume some power depending upon what the R level is. The green OLEDs are going to consume some power depending upon what the value of G is, and these functions are going to be different depending upon the relative efficiency of those OLEDs. But intuitively, you can imagine that this is a very reasonable looking model, right? It's going to be additive, and there's going to be some function f, h, and k. And then we can add these things up over all the pixels in the image, and then there's probably going to be some constant overhead. Where do you think this constant overhead would come from? So I'm basically saying that this, in addition to what is being consumed on this per pixel function, there's also going to be some sort of constant part, just the act of keeping the display on. Huh? Yeah, so it's going to be surrounding electronics, which is reading, writing pixels, this kind of stuff and all, right? So there's going to be some stuff around that. Okay. So essentially, then what one can do is we can kind of your task is to learn f, h, and k, and you can imagine kind of throwing different kind of images at it. Like, for example, set G and B to 0, change R through different values, and do the same game with the other two. And ultimately, you have enough data, and then you fit f, h, and k. It turns out that cubic functions seem to work rather well. So you essentially do a cubic regression over this cubic function, best fit cubic function. Now, this kind of model is a pixel level model. The disadvantage of this is that let's say I give you an image and I say how much energy will it consume to display it for the next 10 seconds, you'll have to kind of do a pixel level analysis out here. So there are more computationally more efficient model that one might want. So direct approach is you add it up at the pixel level, but there are other approaches. So for example, you can do a histogram. Okay, so you can develop a color histogram of the images and then compute the total power by essentially looking at how many pixels are in each bin. So that's one approach. Another way of reducing this thing is by sampling. So instead of adding power over every pixel in the image, you do a random sampling. You select randomly distributed over the image some fraction of the pixels, look at their RGB value and estimate on that basis. And there are different ways, like select pixels periodically in the image, randomly in the image, those kind of things, randomly within a window, randomly globally, things like that. So there are a variety of different approaches people have done for doing this, but kind of the idea is that unlike direct, where we sum energy of all pixels, here we sample and then do it. And there is a final one, which is a code level approach. So kind of the idea out here is that modern GUIs and all, the way they work is that we do not paint arbitrarily over the screen, right? I mean, if you look at your display on your laptop and all, there's some very structured elements out there. There's like a menu bar or dock bar or these kind of things. So these are graphic elements which the screen is composed of. So the image on the screen is not arbitrary collection of, not a collection of arbitrarily drawn pixels, but rather it's a collection of particular type of widgets which have been drawn. So at the code level, you know that. At the code level, you know there is a window composed with a menu, composed with an icon, composed with a dock bar, those kind of things. So if I think of the image, I actually can think of it in terms of these structural elements, and one could associate energy with those structural elements. And then I don't have to do a pixel level accounting for it. So for example, if I knew that the dock bar always takes so much energy, and maybe depending upon how many sort of tabs it has, that would be a function. So you could imagine power models being developed for these different graphical elements, and then you add them up. So that's what this code level approach does, which is basically the code gives you what the GUI layout is, and then there are pre-computed power for each element, and then you kind of compose them up. And of course, if you have something like canvas where an arbitrary image is being shown, then for that you will have to do a pixel level or a pixel or histogram or random sampling kind of stuff. So you can work with that. So this kind of shows that how the accuracy scales, and this shows that how the code level or the image level stuff works. Okay, the main point is that runtime can be significantly reduced. This is a log scale. So instead of looking at every pixel by working at the code level, or by even kind of doing histogramming or other kind of stuff, you can significantly reduce the runtime that you have to do.
Is there any work try to say, okay, this is a picture, and there is a red pixel here, and there is a green pixel here, and the immediate pixel is, for example, blue. If I make it red to decrease the power, the figure will not be affected, but I will save power.
Offhand, I don't know, but people have looked at, and the next slide kind of comes into it, color transformation in context of GUIs. So not in terms of arbitrary images, but this is kind of this is work out of Rice University. So what basically do is, depending upon they kind of looked at, like, could I change the color combination which is being seen. So this, as you can imagine, could be very power hungry because a lot of white and all, but they kind of mess with it, more black dominated, play with different colors and stuff like that, and they did user studies and stuff like that. So we, like I said, some of the Samsung phones, at least I've read, I don't have those phones, but apparently they switch into this black and white mode, which kind of essentially a lower quality GUI when the battery is dying. Now what Amr is saying out here is that perhaps I can even intelligently kind of change the images and all to be more power efficient. And I guess conceivably you could. I mean, dithering and all kind of does that, so you can imagine that as part of that one could do it. In fact, that could be kind of an interesting project idea, which is, are there ways I can transform the image so that they are perceptually still acceptable, but lower the power taken to kind of display them. Okay, that would be kind of the concept. Now, again, these things only matter with OLED displays. That's a very important point, because with LCD, there is no real dependence upon the color. Okay. So that's how the display. It's an interesting area and active area of research in recent times, because display for certain kind of devices, displays are kind of a big power hog. What else do you think you can do with the display to lower the power consumption? Or at least the display system itself, let's say. So display system, I mean the display and the graphics part of it, okay, which also we saw is a power consumer. So we saw color as one, dimming another. What else? Number of frames a second. So in case of video, that would be an issue, because that's kind of stressing the GPU. What else? Maybe use half the screen, something like that, right? I mean, so you can go to a reduced screen, effective screen size, and literally turn off those pixels. With OLEDs, it would work easily. With LCDs, you will need a segmented backlight to kind of make that happen. So these are some of the things that one could potentially kind of play. Other things you can imagine, right now they are changing the color combination of the GUI, but maybe you could also change the structure of the GUI itself. Okay, I mean, it doesn't. So there are other stuff that you can imagine doing it. So display is one of the things which distinguishes portable mobile devices from server type stuff, and that just consumes power. Okay, more generally, as we start looking at post-PC type devices, namely kind of your wearables and sort of carryables and variables and stuff like that, I mean, their power characteristics are different. And so things that were not even present in server and all become kind of an issue. So display was one, but you can also imagine now radios become another issue because they are significantly power consuming, and many of these devices have many radios. I mean, you have your cellular, Wi-Fi, Bluetooth, NFC, perhaps more. Okay, so at least 4 radios, GPS 5. So the couple of things which kind of stick out about these devices. Number one, they have these newer kind of elements, and increasingly for reasons of user interaction, we are also changing them. So like, for example, very common nowadays are things like face recognition, right? I mean, face authentication. So the camera is kind of on because it's okay. So that's one. Also things like where the phone is listening for your command, okay, whatever, hey Siri or whatever, Google Now, those kind of things. So there is again some sort of a speech thing which is always on. So there's a lot of background passive stuff which is happening, and that needs to be kept on. So these sensors and whatever actuators of different types. The other thing is a much larger dynamic range in power demand. We do very dramatically different things and all. Okay, it's while I'm running a nav program on my phone, its power consumption goes up dramatically. My screen is on, the GPS is on, stuff like that. On the other hand, when I'm just listening to music, the screen is shut down, it's playing music, kind of. So huge dynamic range. So the share of classical computing, namely kind of the standard app processor and all, is perhaps less so than some of these communication and media processing type things. And the other thing is that we don't really have hard drives and all of this thing. These are all flash based, so the memory subsystem power has gone down. They're also significantly RAM, the limited RAM. I mean, our laptops are gigabytes of RAM, whereas I guess the highest end smartphones and tablets are around 1 or maybe 1.5 gigabytes, okay, as opposed to 8 to 16 gigabytes, which the laptops are believed to have. And also displays have become simpler, smaller, perhaps even not there in some kind of devices or other kind of displays. Like, for example, Google Glass has a projection display, okay, so it basically projects the image in front of you to kind of hover, okay, so different kind of display technologies. What do you think would be the display characteristic of a Google Glass? So I just said it projects, okay, projects for it to hover at the focusing distance in front of your eye, okay, so you kind of see the image, kind of heads up display. Do you think its power consumption would be higher or lower than a standard display? Okay, so it's light emitting, it's a projector. Well, I mean, our OLEDs and LCDs are also emitting light, so that part is still there. Okay, but it's yeah, Anthony.
Is it higher because it has to be able to work in like the outside the sunlight?
Okay, so it has to be bright and all. That's one part, but there's also the issue of optical loss because it's no longer being on a surface like the thing. It is being projected up in the air. So the distance to that image, there's going to be now a d squared loss which is happening because of that. So as we'll see later, actually, even though Google Glass is such a tiny display and all, it's actually display power consumption is higher than the phones. Okay, so because of these additional kind of factors which come into play. So did you have a question? You were reading it. Right. So if it's being farther out, which is how you will get a bigger image, right? Because it has to be projected farther out, then it's going to take a more hit on the optical loss there. Okay. So kind of things that these devices have to deal with are different, and again the usage range is much more dynamic. Okay, and you kind of see that the absolute power numbers and all are lower out here. One thing interestingly, so see this guy, this thing, and I'll go back a few slides away and stare at these numbers. Where did I have it? This number. Okay, Look at the power supply efficiency here, which is like 90%. Look at the power supply efficiency here. It's like low 80s or even lower. Okay. So part of what you are paying out here is that smaller devices, simpler designs and all are also leading to less efficient power supply systems and all. So, so that's the adapter efficiency. Then you have a second hit on efficiency, which is we use a power adapter which is less efficient, charge the battery, and then we draw from the battery, but the battery has leakage. So your overall end-to-end power efficiency is probably taking a significant hit right between these two elements also. That is, adapter is less efficient, and then I'm losing energy out of leakage from the battery. So let's look at Google Glass for a moment. Okay. So those of you who are not familiar with, I'm sure all of you have heard about it, but essentially deep inside it uses a mobile system on chip, much like our phones. They use OMAP, which is a chip out of TI. At this stage, it's a dead product, both Google Glass and the chip actually, but the chip more so. TI kind of pulled out of this business for the most part. What you have in this thing is kind of battery and stuff like that and all. There's a camera, there's a display, which as I said is a projection display. Architecturally, it is like a smartphone, but without a cellular radios. It basically has Wi-Fi and does it have Wi-Fi? I think it has Wi-Fi. So it certainly talks to your phone. Okay. Main kind of applications are that essentially real-time type information projected in front of your eye. Okay, so you can do communication kind of stuff. You can get notifications and things like that. Okay. So this particular processor has frequency scaling. Actually, one thing which I forgot to mention earlier, but this thing says is that whenever frequency scaling is available, it is not a continuous scaling. It is not that you can pick an arbitrary frequency. You have to pick frequency from a few selected choices, usually order of 10 choices or so, let's say. In this particular case, there are 4 choices available, 300, 600, 800, and 1000. Okay. And kind of essentially behaves for the most part like a smartphone would. So you would see different power consumption profiles, and you see kind of a couple of watt type of, from anywhere from less than half a watt to a couple of watts kind of range, depending upon how many cores are on. So this processor has 2 processor cores, and whether the screen is on or off. Okay. And you could see out here that screen. So these 2 are with screen off, these 2 are with screen on. The screen seems to account. So the display seems to account for I don't know, like 600-700 milliwatts of power consumption. Okay. So power by component, if you were to look at that, so it turns out that the screen power is roughly some baseline power plus kind of a constant term times the multiplied by the brightness of the screen. Okay, so there is a linear dependence on, and it sort of fits pretty well, linear dependence on the brightness of the screen, and then kind of a baseline power. The screen content does not affect the power draw, okay, because it's an LCD display, color doesn't matter. Screen off, the system active around 300 milliwatt. Screen on, but brightness 0. Another 300 milliwatt or so, and that is because the graphics subsystem kicks in at that stage. And then finally, if you do operate at full power, full brightness, then that's another 200 milliwatt or so. So this component, this brightness-related component, in part, is coming because there is a loss in the optical path. So you are projecting out in the distance. There is also color filter, which also results in some loss. And then there is also some reflection in kind of the mirror in the pathway, and also all of them kind of add to loss in the optical pathway. So the upshot is that this number actually changes quite a bit with brightness. By contrast, the iPhone 4 LCD display, which is okay, a couple of generations old, but remains kind of, is basically a lower power consumption. So even though there's a tinier device with a smaller screen and all, but its power consumption is significantly more. Okay, so by the time you add things up, 875, this is 420. So almost factor of 2 more power consumption for this kind of display that you are playing. Speaker. So it uses a bone conduction speaker. So it basically kind of transmits sound into your ear through your bones. Again, as you might imagine, this is a less efficient way of sending power because there's a lot of coupling loss which is happening, and also sort of have to transmit at a higher power. And indeed, it shows roughly 400 milliwatt just for the speaker. The other power consumption unit, so it has an inertial motion unit, so gyroscopes and accelerometers. They consume, there's a microphone, there's a Bluetooth radio, it consumes, there's a Bluetooth LE, and then there is finally Wi-Fi, okay, which is another 600 milliwatts. So all of these are significant components as you kind of add them up. And so depending upon how you are using it, as you might imagine, there is a significant sort of power variation in the power consumption that you're going to see. So how does it look like? If I keep Google Glass idle, it's 22 milliwatt. That's pretty good. You get around 100 hours of battery life. While waking up, so it takes around a couple of seconds to wake up, and while it is waking up, it's consuming 1400 milliwatt. Okay, so a significant bump up because at that time it is activating a lot of stuff. There's just a lot of memory accesses happening and stuff like that. And then let's say after it has woken up, now screen is off, processing on, 300 milliwatt. So it kind of idle 22 milliwatt, the spike and waking up, and then it settles around 300 milliwatt. Okay, so after it in this mode, so it briefly rises to 1 gigahertz. That's when it is doing this, and then it settles at 300 megahertz. So when it is basically in this mode, it's waiting for the user to interact, and it's consuming 300 milliwatt. Then depending upon what is happening on the screen, and so if there is a static card being displayed, okay, so it has this notion of cards which come up on the screen, it consumes around a watt, 2-hour battery life. Swipe through the cards, you swiping action, things trigger in, another 30% more power. Navigate by voice, add another watt. Okay, so the voice is significantly power hungry out here, and what is happening is to do these things, the CPU, either the CPU utilization goes up, so more CPU is being utilized, or the frequency has to be bumped up. Then let's say we are doing even more intense stuff, so like internet browsing, just viewing, scrolling through this thing. All of these things are done, again consume different amount of power. Depending upon the radio also kicks in, so there's CPU utilization as well as kind of the radio comes up. And telephony, so we are using it to talk, around 1.3 milliwatt, and this incidentally is a lot more than if you had a simple Bluetooth headset. So Bluetooth headset is around 100 milliwatt or so. This one is consuming a watt for sort of, if you're simply using a Google Glass and using it for just primarily telephony, it's kind of a bad deal. And then finally, camera system, really power hungry, image, video recording, video call. By the time you are doing video call over Wi-Fi using this, you basically have a less than an hour of battery life. Okay, so pretty power hungry. Taking a picture consumes almost 5 watt for 3 seconds. So so that kind of dictates how many pictures you can take. A lot of this processing increases the CPU frequency and utilization significantly. If you are running a face detection app, then it consumes 100% CPU at 600 megahertz, and in that case, the battery life is less than 40 minutes. So, huge dynamic range. An interesting tidbit, that place where I kind of got this stuff, what they also showed was that there is a significant thermal effect out here. So what these guys do is they start out, and starting out, it's roughly room temperature. Okay. After 10 minutes of operation, it reaches 45 degrees. After 20 minutes of operation, it reaches more than 50 degrees Celsius. Okay, and tissue damage starts happening at around 40 degrees. So kind of another thing is, don't wear Google Glass for long durations of time while doing heavy duty stuff. Okay, I mean, it's sitting against your skin and kind of the temperature is going up. quite significantly. Okay, so anyway, this is actually an issue in general for a lot of electronics, because going back to this thing that our ability to dissipate the heat is kind of an important point. That's how you're going to keep the temperature under control. So wearables are going to face this issue, which is they cannot have the fans and air cooling and these kind of things. Okay. Can you imagine a harder operating environment for electronics than wearables? Can you think of some other kind of devices which are going to be even trickier when it comes to heat removal? Yeah, implantable. The heat has no place to go but to the tissue inside your body. So, in fact, in many of these applications, the limit is often not necessarily the battery life, but your ability to remove the heat. Okay, and that sort of becomes an issue. So, to summarize this part, there are a variety of reasons, variety of subsystems, and these newer devices are doing things differently, and a variety of elements. There is a display part, there's a computation part, there is kind of the thermal aspects and things like that. So next thing I wanted to go over was a part which we have not touched at all, and which is present in a lot of these systems, which is the network, the communication part. So I guess last time around I'd asked kind of just off the cuff that what is more expensive, computing or communication? And I guess I said at the time that communication is more expensive. Even over short distances, communication is more expensive than computing. So let's look at how we can develop a model for power consumption by the communication part of a system. So ultimately, all communication essentially looks kind of like the following. There's going to be some communication channel. It could be, in the simplest case, a point-to-point link. More generally, it could be some sort of a shared link. That shared link could be a coax cable, or it could be air, or it could be something else. Point-to-point link could be a wire, or it could be a directed radio with a very directed antenna. But point is, there's going to be some sort of a shared channel, some kind of channel. So you would probably have some sort of module in software which is doing the channel access. So this is a medium access. You're going to take the data, you're going to encode it, you're going to modulate it into a waveform, convert it to analog, amplify the analog, send it out over the channel, air or wire. On the receive side, you're going to do the opposite. You are going to amplify the signal, which is very tiny. You are going to change its frequency, you are going to digitize it, you are going to now extract the information, and then finally kind of the incoming bits are packetized and sent it out here. So all networking, all communication system at a sufficiently high level of abstraction look basically like this. Now, one thing which has been happening is that this boundary, which is the analog digital boundary, has been changing over time. So it used to be kind of on this side, but had gradually been shifted out here. So anyway, this is how things look like. Now, where does the energy go? So I'm going to talk about this as if in context of radios, but essentially the same concept would apply for other type of networks, in the sense they fundamentally again are sending stuff over some sort of a link, whether it's optical or an electrical wire. Okay. So following is what's going to happen. So imagine I have a sender, I have a receiver. There is incoming information. The sender is going to go through all that stuff I had described, but the final stage is amplifying. So it boosts up the energy in the signal, sends it out over the channel. It traverses over the channel. The channel will see a path loss. So Maxwell's equations, distance travel, so it would be some distance to the power some number. We'll get the signal out here. As long as the signal is of sufficiently high signal to noise ratio, I'm going to be able to successfully demodulate it and decode it and get the outgoing information. So at a very crude level, one can think of three places where I have significant power consumption happening. One is the electronics on the sender side, but we do not include in the electronics the amplifier. The amplifier we consider separately. This is a power amplifier. So it's taking the signal, it's taking the carrier wave of the signal and it's boosting its power up. And then finally, on the receive side, I have the receive side electronics, again, analog and digital out here. Why do you think I would keep this guy separate and not include it as part of the rest of the electronics? I mean, amplifier is also an electronic thing, but can you think of a reason why I'm keeping it separate? Yeah, but still.
It's very high, like compared to the rest of the electronics.
Not necessarily. It's the one thing which depends on the distance, right? I mean, my electronics won't change because of the distance, but this one I need to transmit a higher power if I'm trying to send things over a inferior channel or so longer channel, for example. So this is a term which is distance dependent, but the other two terms are not distance dependent to the first order. Okay, so let me clarify. So sometimes to send data over longer distance, I may have to change the coding scheme, or so in that case, of course, electronics will have to do different amount of work. But all other things being the same, electronics power consumption is not going to depend upon distance. Whereas this guy, if I'm sending things over a longer distance, I have to transmit. I have to spend more power out here. Okay, so what this translates into the following: if I look at the relative contribution of these three parts. So if you look at these plots, and I will warn you about one thing, the Y scales are not the same. It goes up to 600 here, up to 300 here, and up to some 3,000 or something here. No, 8,000? Okay. So if I look at a cellular radio, or GSM radio, or LTE radio, okay, I'm sending over distances which are order of miles. So as you might imagine, all things being same, I mean, these radios work at similar data speeds, megabits or tens of megabits per second. So the first order, the electronics you would expect will not be affected, but it's the power amplifier which takes a hit. So if you see for a long distance radio like GSM, the electronics is tiny, and it's the amplifier power which is the dominating factor. Okay, so I have to send it over a very high power. If on the other hand, I'm looking at, let's say, a wireless LAN, I'm sending over a much shorter distance. My communication algorithms are still of similar complexity. In fact, they may be a little bit higher in the sense that data rates are higher. Wi-Fi now goes up to how much? Anyone? What's the highest rate Wi-Fi currently put there?
300 megabits?
Or there now 1 gig level is the AC, 8.11 AC can go all the way to gig. Point is, it's much higher. Okay, so I expect the electronics might be more power consuming, possibly because it has more sophisticated algorithms operating at a higher rate, but my amplifier power is going to be lowered. And then finally, when you go down to really low level stuff, okay, really short distance stuff like Bluetooth LE or ANT radios or these kind of things, you might imagine that things may even reverse, which is actually RF power may be much less than the electronic power consumption because I'm sending over such short distances, so the d square or whatever, d to the power n loss is very tiny. In fact, this can get so tiny that reception may be more expensive than transmission. Okay, so normally transmission is more expensive than reception because even though so transmission is more expensive because it includes the amplifier. Actually, just a side detour. What do you think would be more complicated? The transmit electronics or the receive electronics? Which power would be more dominating? Which is doing the harder job? Why do you say that? Okay, so we heard transmission, we said the same. What's your answer?
Receive.
You said receive. Okay. Now clearly only one of them can be right, generally speaking. Okay. So equal is very unlikely. So let's rule that out. Okay. So what does a transmitter do? It does encoding, right? So it's basically taking bits and packing them into symbols, doing some sort of a translation, some sort of a coding. What's the reception doing? The reception is getting code words, but they have been corrupted by the noise. And it has to extract the right original word out of it. So while encoding and decoding itself under ideal conditions, you can say maybe they're just symmetric operations. But the receiver is doing something more. It is actually taking corrupted code words and still figuring it out, right? So it's not simply translating them, it's basically also seeing what is the most likely word that would have been transmitted, okay? So it has to do kind of a search algorithm. So if you have done any communication class, you would see that, sort of essentially nearby codes all map to the same word. So there is kind of a search problem that you will have to do at that stage. So it's a more complicated algorithm, intuitively speaking. Okay, I'm kind of glossing over kind of a lot of details, but point is that there's a harder task to do.
Why people go for 10 meters as from figures 50 meters cost less?
Okay, I'll come to that part. Okay, and these are again notional figures. Okay, so again, don't go too much into these numbers per se. The specific numbers were from radios, which were very different purposes. This one was from a MIT radio. This one from an actual Wi-Fi radio. So don't go too much by the absolute number. But there are other reasons also. I mean, these were kind of we'll talk about it, but it turns out that if you look at joules per bit, a more complicated radio can actually be more efficient. Okay, much like a processor. Remember I had said that a higher end processor could actually be more efficient because it has an architectural advantage. So same thing with the radio, it has an architectural advantage. But by the time you hit cellular, distances are so much that that's what dominates. So it's not uncommon to find that for bulk data transfer, your Wi-Fi may actually consume fewer joules per bit than a short-range radio. But where the short-range radio excels is if I have to send a bit infrequently. Okay, so I send it, go to sleep, send it, go to sleep, then this guy will excel. We'll talk about it later. Going back to kind of the thing I was touching upon, so intuitively it stands to reason that receive side electronics is going to be more, generally speaking, more power hungry. And then if on top of it we are operating over short distances, so the amplifier power is very low, so you can enter into this regime where reception is more expensive than transmission. Normally it's the other way around, and in fact much of our communication theory and all has been developed around the proposition that energy is consumed while transmission, and in fact our protocols and all are designed so you sort of try to minimize wasted transmissions. Okay, we try to minimize packet collisions and stuff like that. Okay, whereas once you are in this ultra low distance kind of regime, then you might be in a different regime where, you know, go ahead and transmit redundantly. I have to minimize the reception. Okay, so instead of keeping the receiver up all the time, I'm going to have the receiver being more power managed, but transmission can happen more and more. So it kind of sometimes begin to require kind of a reversal of assumptions that communication in the long distance regime is kind of after. So that's sort of one aspect. The other thing is that kind of in response to our question and all, these radios tend to be more sophisticated. They have more sophisticated coding schemes, they have more sophisticated architectures, so they usually excel if I'm sending a lot of bits. Remember, I had mentioned earlier that again for processors, an 8-bit microcontroller may have lower power, but it may take more energy to do a complicated job. Same thing out here. So this nanojoules per bit is not the whole story, okay? And we'll see kind of that. But main takeaway from out here is that there is a distance-dependent component. That's point number one. Point number two, that this receive electronics generally will consume more power than the transmit electronics. And third is that in a small distance end of things, the receiver may consume more power than these two together. Okay, and in that case, we are into this territory where we need to keep the receiver asleep as much as possible. Okay, as opposed to the transmitter. So radio energy, shouldn't say state of the art. State of the art as like 2 years ago. Slide is a little bit old. But the general trends kind of hold, and I want to sort of bring out some of those points. Okay, So you have GSM, you have A2.11G, A2.15.4, which is the so-called ZigBee, which you find in many products, and I'm showing it at a couple of different power levels. Okay, so the power level, transmit power level is what dictates the distance. So see, here is 30 dBm, here is 16 dBm. Okay, 1 dBm is 10 milliwatts. Okay. So 16 dBm, 0 dBm, and then this is Bluetooth, classical Bluetooth, 15 dBm. Okay, I've given roughly distances they are meant for, so 10 meters here, 100 meters here, 1 mile here, 100 meter here, 1 mile here. Data rates. So one thing you would see is our Wi-Fi is much higher data rate than GSM. You see the receive power, you see the transmit power, and then you finally see the nanojoules per bit. And one of the things you would see again out here is that actually Wi-Fi does pretty good. It actually has the best nanojoules per bit, even better than Bluetooth and all, although normally we think of Bluetooth as a lower power radio. The issue with Bluetooth is that it is low power but not low energy. Okay, it has consequences. The other thing is the way we use this thing. Okay, so Bluetooth excels in rapidly, so for us to be able to shut it down, wake it up, whereas Wi-Fi has kind of more overhead in that direction. Okay, so you would see the story that power consumption is lower out here. So this is 165 milliwatt or 150 milliwatt versus more than a watt, but the data rate is so much higher that the energy per bit is actually pretty good. So what's been happening is that if you look at radios, this is sort of an old Wi-Fi radio, but kind of makes the broader point I want to make kind of holds true for all radios. So very broadly, 3 components. There's a digital part, there's an analog part, and there's a power amplifier part. Analog part does not scale very well with technology, in the sense all those stuff we talked about, voltage scaling, frequency scaling, those kind of things, do not really apply out here. So by doing all our low power tricks, power management tricks, I can drive digital electronics very low, but we'll still be stuck with this, and we still need the power amplifier. So this power amplifier I still need to actually send the signal over the air. That's basic physics, maximum equations. I cannot violate. I have to do that. And there are a couple of things. Firstly, unless I have a very directed antenna, a lot of energy is going towards in directions in space where no one is listening. So that's one issue. The other is the amplifiers can be very, very inefficient. And the reason they can be very inefficient is that the way we send the signal sometimes require that the amplifier be linear. Okay, what does that mean? So an amplifier takes a waveform, outputs an amplified waveform. What would it mean to say an amplifier is linear? Right. So a linear system satisfies linearity properties. Come on, Anthony. Huh? If I feed a signal AX1 plus BX2, the output would be A times the output of 1 plus B times the output of 2. Okay. Main point is that it preserves the amplitude behavior. Okay. So I can carry information which affects the amplitude. In the sense, if information is carried in the amplitude of my signal, then I have to preserve that information, because otherwise a nonlinear system can create a lot of problems. So depending upon where the information is being carried, I may need a linear amplifier, or I may get away with a nonlinear amplifier, an amplifier which is okay. Now we can make nonlinear amplifier extremely efficient, but linearity comes at a cost. So depending upon the type of modulation, namely where the information is being carried, is it being carried in the phase or the amplitude or the frequency of the signal, it's going to affect how efficient an amplifier you have. So this is an old radio, so this efficiency is particularly bad, but so this was maybe 10, 12 years ago. Nowadays it's better, but the point still is linearity comes at a cost, so significant energy is needed here, and significant energy is wasted here. Okay, sort of both those factors come into play. Yeah.
I think if it's also in the frequency and it's not linear, your signal, if it's F1, will be amplified with a small amount.
No, think about it this way: if things are being carried in the timing of the signal, okay, then the amplitude can be corrupted. I can still recover the time. Right? So let's say it was a pulse modulation scheme. Okay, by the way, holds true for frequency also. So in fact, the reason frequency FM radio is better is because even if the amplitude and all are corrupted, I can still extract it. So that's why FM radio is cleaner. Okay, it doesn't carry information and the amplitude on the envelope of the signal. So amplifier has a huge role to play. It's a lot of power out here, and its efficiency depends upon how the information is carried. So upshot of all of this is that we can now begin to develop a power model for our communication system as well, much along the lines of what we had done for our CPU. So what we have out here is, so let's look at different components. Okay, there was a digital, whatever, the electronics part, there is an amplifier part, there is the electronics part out here. Okay, so let's start with this. Okay. So if we look at how the electronics on the transmitter side is going to behave. So imagine along the following: I'm sending packets. My radio was asleep. I decided to send a packet, so I have to wake up the radio. So I'm going to pay some startup cost, and then I'm going to send the packet out. And so what's going to happen is there is going to be a term which depends upon the startup cost of the radio. It's kind of rebooting the radio, and if it needs to register with a base station or synchronize with a base station, all those kind of things, there's going to be some constant term that I'm going to pay, and then I'm going to also pay some actual transmit cost is going to depend upon that plus whatever the electronics is consuming. The amplifier term. So let's assume that we are smart, and what we do is we actually transmit the signal at just the right power so that it reaches the destination. And the destination will require certain minimum amount of signal energy, so that would mean that the power consumption of my amplifier is going to be proportional to some power of the distance. Okay, why do I say power n? Why not d square? We all learned that signals propagate as Maxwell's whatever equation, d square, right? 1 over d square decay. Why am I using d to the power n? Well, okay, so under what condition is a d square valid? Free space, okay? Once you are not in free space, then all these reflections, diffractions, and all that kind of take place. In fact, if I place two radios with antennas very close to the ground, you can show that approximately the channel is d to the power 4. Okay, so if you do not have tall antennas relative to the wavelength, I put two sensor nodes on the ground, okay, they'll actually see a d to the power 4 channel because the ground is reflective of the radio waves at the frequencies we operate at. More generally, when you're operating in an urban terrain and all, or like walls and stuff like that, there is a lot of other effects are happening because of the non-free space aspects, and therefore that usually gets captured in by saying that my decay is something more than 2. Very common in our kind of indoor office buildings, urban terrain and all is that n might be 4, 5, or 6, something like that. Okay, let's say 4 to 5, something like that. Okay, so it's pretty steep decay. Receiver electronics, same kind of structure with same kind of thing in the transmit side, which is there is going to be a startup component, and then there is going to be the actual electronic component out here. Okay, and the n over r refers to the following: that n is how many bits I am sending, and r is the rate at which I'm sending. So kind of the idea is, if I'm sending it a faster rate, I'm going to be able to do it over a shorter period of time. But then I'm also, and n is the number of bits I'm sending. Okay, so that's the effect which comes into play. You'll also have digital processing supporting this stuff. So if you think about it, the digital part of electronics is going to be our good old models, CV square related models, leakage related models. So all of that will come into play. And then my amplifier is probably also going to have some sort of a constant term plus some term which is actually proportional to the power. Okay, so just the mere act of my amplifier is not energy proportional. So even when I'm transmitting it at a very low setting, it will still consume, its electronics is going to consume some power. So all these different components, one can attempt to model it. You can reduce all of it down to a very simple model. It basically says energy to transmit a bit is alpha plus beta d to the power n. Alpha is some constant which is capturing all those electronics and all, and d to the power n is because of the amplifier, and beta is something to do with the amplifier. What do you think the energy to receive a bit will look like? Like, what's the simplest model you can think of? This should give a clue. So transmitter beta is alpha plus beta d to the power n. I'm kind of pushing everything under kind of a constant term which is distance independent and a term which is depends on the distance. What about the receive side?
Alpha then beta n.
Huh?
Alpha plus beta n.
Alpha plus beta n. No, so we are talking about per bit.
N is the number of bits.
Okay, so it's just going to be some constant gamma. That's it. So energy per bit on the receive side, a good first order model is some constant term gamma. Okay, assuming a particular rate and stuff like that. Okay, once we change the rate and all, then the frequency will have to change. Things will happen. But given a radio at a particular setting, energy to transmit, the alpha terms refers to all the electronics, and also that's like my static power because of the static power. Think of it like distance independent term, and then this is the term which is distance dependent, and then for the receive side, it's going to be some distance independent term.
In this model, you are assuming that the sender is smart enough so that you can expect the D.
Right. I am assuming that the sender is smart, that it sends just the right amount of power to reach a particular D. If, let's say, the sender is stupid and sends the radio at a maximum power, okay, is not able or be conservative, then this would be instead of actual D, it will be D max, whatever is the range of the radio. In that case, this will reduce to again a constant term. Okay.
And if it's lower the edge, I think the receiver also will make something in terms of distance as you want to understand.
Receiver to the first order is distance independent, but that's not entirely true. Why not?
Amplifier.
No, there's no. Oh, you're talking about the tiny. Yeah, but that amplifier is very. I mean, it's not the dominating factor. Let's say.
Does the receiver power? Does the noise vary on the distance? Well, that's what the effect is.
You could imagine that worse channel would make the receiver's job harder. It may have the algorithm may spend more time decoding than if it was a clean channel and therefore easily decodable, right? I mean, so yeah, you could algorithm may take a computationally more expensive path. Okay, whether it's true or not depends upon the specific radio and all, but you could imagine that under bad channel conditions, it may just have to put in more work. Okay, than otherwise. So switching back out here, so essentially a good. Did you have further question? Oh, okay, so switching back out here, so a good model of the radio is, a good first order model of the radio is, that is alpha plus beta d to the power n. So I can characterize the radio or essentially any transmitter in terms of these alpha and beta. And this is kind of a bunch of different radios, somewhat old radios, but point I wanted to make was that look at alpha and beta out here. So this is like a garage door opener type radio, okay? 14 microjoule plus 3.1 microjoule. So essentially we are looking at some microjoule per bit, okay? By contrast, computing was much more efficient. Okay. This is looking at another kind of low-end radio. It's like point 0.4 microjoule or something like that. So more efficient than this, but still. This is some custom radio out of MIT. This is a Wi-Fi radio. This is actually a 802.11a radio, and actually of the lot, you would see that this guy is actually the most efficient. 14 nanojoule and 11 nanojoule. So this goes back to this point that the place where it is getting its efficiency is because its data rate is so high. But if I were to use the same radio in a setting where I was sending a small number of bits, going back to sleep, waking up, sending a small number of bits, then it would actually be quite inefficient. Okay, its efficiency comes when the startup cost has disappeared. Okay, so that E start that I had out here, that is very tiny because it gets amortized over a lot of bits. So if I'm sending kind of lots of back-to-back packets, I end up having I end up sort of asymptotically approach this thing. Yeah, so one way of thinking about it is a bad channel increases the effective D. Okay, so if I'm actually traversing a particular distance, but if the channel is bad, then it's as if I'm traveling over a longer D. That's one way of thinking about it.
But if the channel is occupied and you have to back off.
Oh, okay. So the way to think about it is that if my channel has congestion, then to get a bit across, I may actually have to send more bits. That's one way. So this is this notion of throughput versus good put. Okay, that is a good throughput. So not every bit that I am sending is necessarily advancing, resulting in information reaching on the other side. So if the channel is congested, you can translate that into saying that for every bit of information, I have to actually transmit some more bits. So if there would be a multiplicative factor which you can add around it, so you could say alpha and beta both go up proportionately, which by a factor which corresponds to the congestion. Okay, and you could do it by for simplified models where for a particular level of congestion, you can figure out what is the probability I'm going to actually get access to the channel, and based upon that, work out that how many attempts it would take for me to kind of send things out. There's another factor also which affects things. So not all bits we send are useful bits. Let's take something like, I mentioned ZigBee radios earlier on. So in case of ZigBee radios, my payload is relatively small, but the header is relatively huge. So you might have this situation where, let's say I have a sensor which is sending temperature reading, maybe a couple of bytes, but the header itself might be 32 bytes or something like that. I think in ZigBee is something like that. Okay, so just to send a couple of bits every so often, I'm actually sending 10-15 times more bits for the header part of it. So that would also, if you think in terms of energy per useful bit, then there would again be kind of a multiplicative factor. And what that would mean is that if I am sending a lot of information, then the overhead will get amortized. So congestion, the size of the packet, all of them you can think in terms of multiplicative factors kind of kicking it out here. Okay. Very common model of radios previously used to be kind of a unit disk model where you basically say that transmit cost certain number of certain energy per bit, but it's not necessarily always the case because of this distance effect that comes into play. Any other question? Okay, so this also leads to kind of some insight into what might some of the things one can potentially do in terms of a transmission strategy. So let's say I have a radio whose energy model looks like this. So alpha 1 plus alpha 2 to the power n. Okay, so alpha beta I have these two terms. And my job is to send that bit from source to destination over a distance d. So I could do it in a single hop, or I can do it in multiple hops. If I do it in multiple hops, so let's imagine I just do it in multiple equal hops. So I'm doing it, I have two relays out here, so I will have 3 hops. The point is each one of these is going to be some hop distance. So now I have alpha 1 plus alpha 2. The distance gets divided by the number of hops, but I have number of hops as a multiplicative factor. And essentially, depending upon alpha 1 and alpha 2, and depending upon this coefficient out here, I may come out ahead or not. Okay, so upshot is that for very small distances, single hop would be good, but for larger distances, having number of hops increase would be beneficial. And you could imagine that I can essentially do a optimization of this function to come up with a optimum number of hops, which would kind of which basically end up looking, which are a function of alpha 1 and alpha 2, assuming 2 out here, the distance power. If it is n, then that will also enter out here. So this shows out here what's happening is that as I'm increasing the distance, we start out 1 hop being the most efficient, then the blue, which is 2 hops, become most efficient, then the green, which is 3 hop, and finally 4, which is the 4 hops case. So the longer the distance, more the number of hops would be beneficial. So what that means is, for example, for systems like cellular phones and all, one way of reducing power would be that if we actually can send to some intermediate device and then, or a nearby base station. So this is what leads to these concepts like femtocells and micro base stations and all, which are all dealing with this notion that instead of having few long distance base stations, I can have lots of shorter range distances and come out sort of save power consumption, and by the way also increase the spectrum capacity as a result. So this basically makes the case that multi-hop sort of helps. It in turn creates other complications. It makes networking a nightmare. So left unsaid in this thing is that while this is all nice, the problem is that maybe it increases congestion, maybe it increases all those overheads. So now to send a bit successfully across n hops, maybe I need to take a lot more extra bits, and therefore the benefit out here may get negated, and that's kind of I guess from a theoretical perspective not as satisfactorily understood as one might imagine. There's a lot of experimental work and all, but multi-hop comes at increased complexity. Increased complexity results in more bits being sent to get the same good bit across, and therefore the effective, there is a negative counteracting term which kind of comes in out here, which one has to factor in, but this simple model does not. But ignoring those issues, if you were to simply look in terms of a bit sent across, then multi-hop at certain distances is going to be beneficial. One other thing which I had touched upon in the equation out here, which is this role of startup. So the issue out here is that every time I send out a bit, I have to, if my radio was asleep, I'll have to wake up the radio, I'll have to send some extra bits to lock the channel as header and stuff like that. So what ends up, you can capture all of that as some sort of a startup cost. And if I'm sending large amount of data every time, then the effect of that startup will disappear. It will be amortized over lots of bits. But usually I do not. So therefore one has to also account for this. So what kind of stuff we are talking about? So this is some radio where transmit power is 80 milliwatt, receive power is 180 milliwatt. Okay, this is an example where receive power is more, and then the startup cost is around half a millisecond. Okay, half a millisecond is fair bit. Okay, so essentially every time I'm sending a packet, I'm to wake up the radio, I'm setting this thing up. In some radios it can be even worse because they may have to handshake with the base station, establish a connection before the data can go out. So if I'm sending data sporadically, then these startup costs can begin to dominate. So for applications like sensors and all, where you're sending data rarely, it is quite necessary that the startup cost be kept very low. That is, I design systems, I design radios which can wake up very rapidly, quickly send the data, go back to sleep. So all that handshaking and all they have to do should be kept to minimal. This is equivalent to saying that if I am designing a processor which has to do sporadic activity, once in a while it has to wake up, process a sensor data and do something, I better make sure that the wake up cost is kept as small as possible. The OS should not take an hour to reboot or whatever, 10 seconds to reboot for me to do a millisecond of work, because then I'm going to pay that 10 seconds all the time. So when it comes to these systems, it's important to not only think in terms of what their power consumption is, or for that matter, how much energy they need to take to do some amount of work, but also how much energy and time they take to wake up and to sleep. Because depending upon how often your workload is coming, that may become dominating factor, or what is the size of your workload. Okay, if I'm sending 1 bit at a time sporadically versus large images, okay, then that amortization will come into play. And the startup cost is entirely wasted energy, because we are basically paying for it. So if my packets are small, then I'm basically amortizing them over fewer useful bits, so my energy per bit is kind of going to go up quite a bit. So what you see out here is that as packet size increases, energy per bit goes down. Okay, and part of the reason Wi-Fi also does very well is because it has larger packets than, let's say, Bluetooth. So even though Bluetooth was lower power, its lower rate and a smaller packet size both kind of ended up hurting. So anyway, that's kind of a story on the radio side of things. So again, much like the processor, we can have relatively simple models to do a good first order job. There are more accurate models. So there are papers which go into still abstract but more detailed models, where you can feed all sort of parameters. What's the data rate? What's the packet size? All those kind of things. So models get somewhat more complicated, but you can nevertheless kind of look at the broad trends. And the broadest trend to kind of think about is that there is a distance independent term and there is a distance dependent term. But there will also be terms which are going to correspond to channel conditions, so which will affect the alphas and the betas. There is going to be stuff about the data rates. It's going to affect the alpha and the beta. All those terms kind of are going to be on top of it. So let's stop out here. On Thursday, we are going to continue this. So we're going to look at more now how all these models translate into kind of a complete system.